In this video, we are going to demonstrate the detection and mitigation of DDoS attacks in 5G V2X networks. In general terms, we deploy a deep learning-based model to detect the attacker and a sinkhole-type slice to limit its traffic to a maximum level. 4 different scenarios are deployed on our 5G V2X platform, where we perform a lane-changing overtaking mobility behavior with 2 robot cars and DDoS attacks with a third one located outside the road. As a first step, we launch each one of the 5G V2X platform's main elements. The first element is the 5G core network, which is based on Docker containers. Once all core modules are started, we launch the real-time log that shows the Gnode Bs and UEs that are connected. Both tables are empty in this phase, since we did not start them yet. In the following step, we launch the FlexRig controller and the Gnode B, which are located in a separate machine, but in the same local network. Once the Gnode B is connected, it's immediately recognized by FlexRig and the core. Once we have all run and core elements up and running, we proceed to the connection of each one of the UEs, that is, the robot cars. We start by turning on the 5G card on top of the first robot car. After a couple of seconds, the green light indicates the beginning of the authentication procedure, as we also see in the Gnode B and the core terminals. In order to conclude the robot car's connection procedure on its terminal, we launch a command to start a PDU session and then obtain an IP address. The same connection procedure is repeated to the other 2 robot cars. As a last step for the 5G V2X platform's startup procedure, we launch a remote server on the 5G core, whose main role is receiving requests from the robot cars concerning the mobility decisions to be taken in real time. The mobility decisions are essentially composed of steering and throttle values. After each image collected and processed by the autonomous mobility model, the robot car requests a confirmation to the remote server before applying the respective decision. If no reply is received from the remote server, the robot car takes the last reply decision. We now proceed to the first out of 4 scenarios that we are going to present in this video. This first scenario concerns a normal use case, where no DDoS attacks are deployed. Here, 2 robot cars are on the road. One of the robot cars changes lanes over time, but without overtaking the other robot car. We place both robots in their starting position on the right lane, then we proceed to launch the autonomous mobility model on each one. The model's startup procedure is finished once we see the images being captured by both cameras. At the same time, we see the mobility decision requests being received by the remote server. As we see in the video, one of the robot cars moves to the left lane, and after some time, it goes back to the right lane. The second scenario still concerns the absence of DDoS attacks, where one of the robot cars performs a full lane overtaking. The robot cars are placed at the same startup position as for the previous scenario. After a few moments, the robot car behind moves to the left lane, it overtakes the other robot car, then it moves back to the right lane, hence concluding the overtaking procedure. As a third scenario, we show 2 sub-use cases where a DDoS attack is deployed. The first one shows a collision between the robot cars, and the second one shows one of the robot cars leaving the road. Both sub-use cases are caused by the DDoS attack, given the lack of communication between the robot cars and the remote server. To launch the DDoS attack, we use a third robot car placed outside the road. From its terminal, and during a lane overtaking procedure, we launch a tool called mousetsun that injects a large number of TCP SYN packets towards the remote server. As mentioned previously, the communication between the robot cars and the remote server is disrupted and the accident happens. The same behavior may be observed in the second sub-use case, where the robot car leaves the road. The fourth and last scenario still concerns the deployment of a DDoS attack, but this time the attack detection and mitigation module is also launched. Contrarily to the previous scenario, once a DDoS attack is deployed and the robot cars cannot communicate with the remote server, they immediately stop on the road. Their trajectory will be resumed once the communication with the remote server is reestablished. As we can see in the video, once the DDoS attack happens, both robot cars immediately stop and the detection module is launched at the 5G core. As a first step, it performs a network packet capture between the robot cars and the remote server. Such packet capture is applied as an input in the detection module. After processing the data, the model provides an output indicating that a DDoS attack is happening, hence creating a sinkhole-type slice. In the following step, the detection module proceeds to identify the attacker's IP address. Once this is done, the attacker is moved to the sinkhole-type slice, thus limiting its traffic to a maximal level. This allows reestablishing the traffic between the robot cars and the remote server, which allows them to resume their trajectory on the road. In this video, we presented 4 different scenarios deployed on our 5G-V2X platform, where we perform a lane-changing overtaking mobility behavior with 2 robot cars and DDoS attacks with a third one located outside the road. The attacks are detected and mitigated in real time by isolating the attacker in a sinkhole-type slice, hence limiting its traffic and allowing benign users to continue their trajectory.